Hi there, this is Group 5 and I am Xiaoyi. We have 3 members in total. I will start firstly and Hongyi and Zirui will present according to the order. Today our topic is to find the relationships between hostel prices and different features in Japan. As we all know, Japan will hold Olympic Games in 2020, and as it usually provides economic stimulus, there will be 20 million tourists by then, and as many as 8.5 million foreigner tourists will project to visit the country during the Olympic. With these large amounts of tourists pouring in, accommodation becomes a question that tourists and operators need to think about. And we are going to figure out what are the different factors driving up these costs, and then using multiple linear regression to find a relationship between various features and the hostel prices. Those information could be really helpful for tourists to realize which factors affect the price most and to determine whether to pay for that or not. Also, it's useful for operators to consider about how to get better benefits by devoting more on which factors. Now let's take a look at our data. It is from Kaggle website, which gives us prices of hostel under various situations, mainly in Tokyo, Kyoto, and Osaka. We have 8 numerical variables, namely staff, distance, summary score, cleanliness, facilities, location, security, and minimum price, and also 1 categorical variable, which is city. We have used numerical values to quantify our categorical variables to help with our model selection process. We assigned 2 variables, x8 and x9, to represent city. In this project, minimum price is treated as response variable and others as explanatory variables. Then we did some pre-analysis to select model. Firstly, we constructed the correlation matrix, as we can see in the right-hand side, to get a broad view about the correlation between variables. As shown in the correlation matrix, response variable seems to have minor linear relationship with all other variables except the x8 and cleanliness. Besides, multi-collinearity exists between explanatory variables, especially with security, staff, cleanliness, and summary score. The scatter plot further proves our conclusion that the response variable is not having linear relationship with all other variables. However, there is a clear association between some explanatory variables, which indicates multi-collinearity. When we did a box plot in the left-hand side, we can tell that among all 3 main cities, the hostel prices distributed normally except for several outliers, which have been plotted as individual points, are a lot more than normal prices in Osaka and Tokyo. Then we did the ANOVA of the full model. This seems to be a bad model since the R-square adjusted value is really low, about 0.1015. The p-values for all the explanatory variables, except distance and security, is really large, indicating a weak linear relationship with the response variable. We conclude that the data might not be suitable for the linear regression, but we continue to improve our model by transformation and other model selection methods. In addition, histograms of predictors were generated and carefully checked. The histogram revealed that the distributions of these predictors, like facilities, location, and security, and somehow problematic, being either extremely skewed or almost discontinuous with 2 models. In this regard, we were considering to drop facilities, location, and security from our model. In addition, we did residual plots before and after dropping 3 variables mentioned before. As we can see, the points in the residual plot are sort of randomly dispersed around the horizontal axis, with only few outliers. We can see that this linear regression model is appropriate for the data. We just have to deal with the slight non-constant variance of the residuals. Then, as we could see generally in the residual plots for several individual variables, most of the points are distributed flatly along with the horizontal axis, except for several outliers way above the normal. We could also say that this linear regression model is appropriate for the data. Lastly, we did the QQ plot, as we could tell from it, which indicates right skewness in our model but still support normality. Now I will hand over to Hongyan. Since we figured out that our model is right-scaled, then we conducted the box cost transformation analysis for the response variables. As the left graph shows, the best lambda value seems to be around negative 0.2. After the box cost transformation, we found the ANOVA table of the model and noticed the R-squared adjusted value of the model changed to 0.1219 with an improvement of 0.0204 for all the explanatory variables. P-value decreases, which means they have more correlated with the response variable. The p-value of the facilities, locations, and securities are still very high. Therefore, we decided to drop these three variables. After Y transformation, we use the three methods for model selection process, which are the best subset algorithm, stepwise regression method, and model validation. Firstly, we use the best subsets. The first picture on the left shows the result. Based on the result, model 4 has the greatest number of the best value among all the 9 models. At the same time, the SSEP and R-square of the model 9 are the greatest. But that's because as more predictors are added to the model, the SSEP will always decrease and the R-square will always increase. Model 6 has the best adjusted R-square value and Model 2 has the best SBCP value. Model 4 seems to be the best one we might to choose. In addition, we use the stepwise regression method, and the picture on the right presents its result. You can see there are 3 steps in process which detected 3 explanatory variables: facilities, locations, and security. These 3 variables have the 3 top p-value in ANOVA table after box cost transformation. The 2 analyses came out with the same result, but the model generated by the stepwise regression method is model 6. Since we're still not sure which method we should use, we did the model validation to find the final analysis or model selection. As the second picture on the left shows, the RMSE value for model 4 is less than model 6. While there is only a minor difference in RMSE for these 2 models, and we believe summary scores and staff scores have association with minimum price. In the end, we decided to use model 6 as our final model. After finishing model selection, we used the diagnostics to test the model that we selected. As we can see from the test that's showing on this page, the residual plot of predicted value appears to be approximately normal with a constant variance. Also, the BF test shows the difference is statistically significant because the p-value is much smaller than the significant confidence. The QQ plot appears to almost follow in the straight line, as well as the p-value in the Shapiro-Wilk test is larger than significant confidence, that showing the residuals are mostly normally distributed. After VIF test, we could see from the result that the model is now free from multicollinearity. In the end, we refined the model by checking and selecting some outliers from the dataset. Cook's distance, student height, selected residuals, and DF betas were used as a combination to search for outliers. It turned out that this matrix suggests detecting a significantly large portion of data, and many of them tend to come consecutively. In terms of outliers and inflection points, we decided to go with a theoretically value cutoff, which is 4 over n minus p. So this this would mean the cutoff would be around 0.015, and this resulted in about 40 influential points being removed. This is illustrated in the plot, and you can see here that we have a number of outliers. Then Ziren will conclude the last part.
After all the diagnostic and model selection process, this is our final model. Minimum price to the negative 0.2 power equals distance plus summary scores plus cleanliness plus staff plus x8 and x9. Below is the ANOVA table for the final model. From the large f value and the low p-value, we can deduce that except the distance, all the other explanatory variables are significant or have association with the response variable. On the right is the residue plot. From the plot, we can see that there is no non-constant variance problem, and the best fitted line is nearly a straight line, which means there is no dependence between variables and in a y value, which means our model has a good fit. We also did some analysis on the normality of our final model. Here is a histogram. From the histogram, we can see that our model is kind of normal, although there are more data above the mean. Below is the confidence interval of our explanatory variables with specified confidence level. We can see that the confidence interval are relatively narrow, so our model has a great prediction. On the right hand side is a summary of our final model. From the t-value and the p-value, we can also deduce that all the explanatory variables have association with our response variable. From the adjusted R-squared value, which is 0.1248, we can see that it is relatively small compared to other models, but we have improved it a lot from our original model. The low adjusted R-squared value indicates that our model might not be appropriate for the linear regression. Maybe other regression models are more appropriate, more suitable for this data set. This is the discussion section. Our final model has low adjusted R-squared value, and most predictors are statistically significant with p-values smaller than 0.05. The residue plot appears to be both constant and normal, showing no sign of violation of typical assumptions. From the ANOVA table, distance and summary score contributes positively to the hotel price, while cleanliness, staff, X8 and X9 have a negative contribution, which means as cleanliness, staff, X9 and X8 increases, the minimum price of the hotel actually decreases, which is a new discovery of our project. In the end, the parameters are kind of small. For example, the correlation coefficient, which means some of our explanatory variables may have a minor influence on the response variable, which is the minimum price. Here is some of our conclusions of the project. We conclude that this model can be used to predict the hotel price in Japan, show clearly the relationship between different features and prices after we eliminated some unrelated variables. But we believe there should be another model that can better explain the relationship, because the R-squared value is still very small. For the model selection section, we used the best subset test and the stepwise method. to figure out which model should we select. And the sixth model is the best one from our opinion. For diagnostics and remedy parts, we find out two problems, which are the non-constant variance and the not normal residue plot. And we used several methods described in the previous slides to figure out how to solve them. Our model validation results indicates the model's strength. We have an R-squared value of 0.1248 for the transformed model and 0.1015 from the initial full model. After all the diagnostic, model selection, and transformation, we clearly have increased the R-squared value a lot. These are the two references we used. And thanks for listening.